Yeah, so welcome back. As I was saying, I've kept this session very open-ended. If you were here physically, then we could have gone over each desk and done a real a physical hands-on session. Um, Now here, in this case, I'm going to do so. I'll do it in the following way. I'll take some problems and I will try to solve these. Start my video momentarily. Yeah. So I will take a few problems and I will try to solve these or go through the steps that are needed. Now I'm using the Matlab Toolbox, the system identification toolbox in Matlab. Whenever I've given projects to students, they have all preferred using Python and or R. So almost everything that we are showing here can be accomplished in Python or R, and that is not a limitation of what we are going to do. So, for example, if you see, so in Python, R, and even in Octave, there are a lot of packages. So you need to be able to download the correct packages so that you can accomplish what you are trying to do. So, for example, if you want to do autocorrelation, then you will need to know how to do that, or if you're trying to look at a power spectrum, you'll need to see how to do that. If you're trying to identify given data, identify ARX model, again, you will need to see which package and how to do that. But I have myself played around with R quite a bit, and I have not found it to be a limitation because there's so much information on the web that you can almost always figure out how to take it forward. Okay, so as I said, I'm keeping this very open-ended. So let me start by sharing my screen. And what I can do is probably look, so I'll stop my video. If that takes up away my bandwidth. Um, so the first thing that I will do is just complete. Uh, so we've looked at ARX, we looked at OE. Okay, let me just look at RMAX. So as I was trying to say that, see if I can make this. Okay. So I continue working on this. So um, as I told you, there are two family of models for time series, in case of time series models. And uh, how do I write in this font? How can I write? I'm not able to write on this. Okay, there you go. And yeah. So uh, as I was saying that there are really two types of models. One are the output error family of models and the equation error family of models. Okay. So let's just quickly recollect that if I gave you uh, y is equal to b by a times u. This is what I was interested in. But there is some error somewhere. And I need to be able to see how I model that error. So if I think of that error in the output y, so I say, no, my error is y minus b by a times u, then it becomes an output error family of models. If I model it like this and say that this is an equivalent minus bu, and therein is the error, then it becomes an equation error model. Okay, so there are just two broad families of models. So now, if so, I will write this as my error epsilon, and here I'll write this as my error epsilon. So let's start with ARX. Sorry, with the output error family of models. So if I say my epsilon is equal to white noise E, then this is known as an output error model. Now, if you are telling, this the name of the family of models is also output error, and the particular model is also output error. Like, you go to some place, the name of the state or the district and name of the city is same. So it's like that. Okay. So this is the case where you have epsilon, you're modeling it as white noise. That gives you the output error model. So therefore, what is the output error model? It is simply y is equal to b by a, okay, times u plus e. This is the output error model. Okay. Yet another way. See, we saw about, we talked uh, about white noise. Okay. What if, no, I say, no, this is not how I want to model my epsilon. I wonder how do I go page up. I now remember that I used to use OneNote app, and here I'm trying to use OneNote as on the web. So, uh, so anyway, so this is my one type of model. My second type of model is if I could simply say that my epsilon, okay, is itself a time series model, which means my epsilon, I'm going to model it as, let's say, C by D times E of t. You see the difference? In one case, you have epsilon is simply E of t. That was output error model. In the second case, I am modeling a numerator over denominator. In this case, you will therefore see that my model will become of the following type. I will write the full model. So y of t is equal to, oops, uh, okay, y of t is equal to, uh, okay, let me just add a page. Okay, so I have y of t is equal to b by a times u plus c by d times e of t. Okay, this is known as a very famous model type called Box-Jenkins model. Okay, and was used in and these time series models are also used for modeling financial, like I've seen time series models used for modeling economy of a country and so on. They're also, of course, very, very popular for modeling stock exchange kind of data or any other time series data. So, so this is known as a Box-Jenkins model. And so you see that this is your epsilon. It is over here. So this is also an output error family of model. Okay. My second family of models, as I told you, was equation error family of models. Okay, so it is equation error family of models. And here I will model AY. I'm not happy with this font over here. Is equal to epsilon. So if I put this as E of t, I get what is known as the ARX model. Okay, in equation error family of models. If I had, on the other hand, put AY minus BU is equal to times E of t. So I'm saying that it is a moving average. This is known as a moving average. Why? Because C is what? C is 1 plus C1 Q inverse and so on. So we will see that, oh, it is E of t plus C1 times E of t minus 1 plus C2 times E of t minus 2. So it's a moving average. Okay. And because of that, we call this as the Armax model. So this AR is still standing for auto regression, that Y depends on its own previous values, and X stands for that external input, and this stands for the moving average of white noise. So these are known as Armax models. Okay, and this is another way of modeling that noise. Now there might be certain models now which fall in both the categories. Okay, and one of them is known as the finite impulse response model. So for example, if I say that AY, or I'm sorry, I'm not very happy with the way this is happening. Let me just start a new page. So if I say y of t is equal to b times u of t plus e of t, okay, this, if you see, can be written. So I had told you there are two families, right? Either you write ay minus bu, or you write y minus b by a times u. You see, in this model, a is 1, okay, and c is 1. So you can either write it like this, y of t minus bu of t, because a is 1, it also becomes y minus b by 1 times u of t, which was the output error family of models. So this is known as an FIR model, and it belongs to both the families. Okay, and these are amongst the most popular models that, if you are trying to use data to be able to identify. So that was the first thing I wanted to complete some more family of models. I will now attempt to, maybe we can just try out certain things. So the first thing that we could try is simply look at that noise. Okay, so the first thing that I could try is look at white noise. So let us try to model or try to draw white noise. So you remember that E of t. So what is the use of this E of t? If you recall, is how do you model that which I cannot explain through U? So how can I model that part of Y which is not explained by U? And we decided that we will put a placeholder. The placeholder was really, shall I just go back to and maybe just insert a slide here or something? New slide. Then make this full screen. Okay. So let me look at that noise. So this is the first thing we are trying, okay, on our hands-on session. That is white noise. So just to recap, what was white noise? We said Y is equal to GU, the input-output relationship, plus some V of T. This is that inexplicable, don't understand why Y is behaving like that, and we put a placeholder. We say, okay, just put everything in V. The question is, how do you model V? And in all cases, our model of V, whether it was an ARX model or an Armax model, you can always write it as Y is equal to GU plus V. And this V, I model it as white noise, which is driven by a linear system. So H is something like C by D or 1 by C. So it's some rational transfer function. Okay. So this is what that inexplicable part is. It is this over here, V of t, which is the output. And how do we model it? Model it as a linear system driven by white noise. This is H. H is what? H is just some C by D, or just C, or 1 by D, some rational function, transfer function. And you all know now C, when I say, I mean really C as a, it's a function of that backward shift operator. So you have some H of Q inverse. So this placeholder is modeled in a very specific way in these time series models. So, there are always questions, under what conditions will time series models not work? And then you have, appropriate theory that tries to answer those kind of questions. So we want to now see in our first step, what is this E of T? And under what conditions, what type of V's can it engender? Okay. So the first thing we will do is draw E of T just to see what does this look like. Then we will look at the autocorrelation. And I have already told you that this autocorrelation is the direct delta. That is, it will look like this. This is tau, this is 0, this is 1, this is minus 1. Remember that the autocorrelation is a symmetric function, because it really doesn't matter whether you took expected value of E of T into E of T plus tau, or you took the value of this as E of T into E of T minus tau, because it's the same signal E. Not true about cross correlation. So we'll try to draw E of T, then we'll try to find what is R of E. I think, I also have a power spectrum. So we'll try to draw the power spectrum of this, which, as I told you, is the Fourier transform of the autocorrelation function. So it is, and this all you can do in any software. Okay, so let this be our first attempt. So I'm going to go back to, maybe we can keep this. What I will do is go to Matlab. Okay, now I do have codes which I share with students and to show. I do have a lot of codes which do this, but let's do it, one at a time. So, how many of you have Matlab or at your disposal right now? Is there? So, depending on that, we could either I can just do a demo and not a hands-on, or we could do a hands-on. So if, okay. Okay, so, that's okay. I mean, if you have also, that's okay. So what I'm going to do now is first, how do I get this white noise? So you remember that we had looked at different densities in the first class. And one way of, and I think Professor Manibhushan also talked about how to generate densities from some random probability density function. So one specific dedicated for normal random variables is known as randn. Okay, so what we can do is generate this. So this command will basically generate 2048, that is 2 to the power of 11 samples, and let's just evaluate that part. So the great thing is, I was going to tell you, the great thing is it works so fast, and it took some time. I don't know why. So now you could just plot this E. So I could, for example, evaluate E. Oh, I should have, let me just clear all. I was just playing around with. Okay. So, I have also defined something called a sampling period TS. I have also defined something called a frequency, which is 1 by TS. Okay. So this is how white noise looks. It is, as we said, it is an uncorrelated signal. I hope it is showing. And if I blow up some small part of it, it is exactly what I said. That given E of T, I don't know what is 1 or E of T plus 1. It could go anyway. That means to say that E of T plus 1 is not correlated with E of T. Therefore, E of T plus 2 is not correlated with E of T. Okay. Therefore, the autocorrelation for any lag, that tau is often known as a lag, is always going to be uh, is always going to be 0. R e of tau is a direct delta function. Okay. Now um, I share these codes with you so you can also play around with them. Now I want to be able to find colored noise. Okay, let's go back over here and look at what a colored noise is. So colored noise means that there exists some kind of a correlation. So in case of white noise, we said E of k plus 1 and E of k, there is no connection. They are not talking to each other. But in colored noise, there is a correlation. There is autocorrelation. And so here, E of k plus 1 depends on E of k. Okay. And the question is, oh, does E of k plus 2 also depend on E of k? So here the lag is 1. Tau is equal to 1. If E of k plus 2 also depends on E of k, then you will say that, Re of, this will look at Re of 1, this will look at Re of 2, and so on. Now if it is a stable system, we all know that eventually the initial condition effect wears out. So you might find that if you were to do enough of these, you might find that E k of plus 1000 may not depend on E of k. Okay. So this might be significant, this might be good, and this might be close to 0. So then I will see, and of course, Re of 0 can never be 0, right? Because the value E of k depends on the value E of k itself. In fact, they're identical. So you always find, for a stable system, that this one, not always true, that for a stable system, but for the most part, you will find some wearing out effect like this. If it is periodic, then you find this Re to be also cycling, and so on. Okay. So having seen, the question is, how do we generate that? And so what I will do as a trick, I will do V of t, and let's just look at our Matlab. So we will generate this colored noise, okay, by correlating it like this. As maybe you can see on the screen, but let me just go back and write it down on my
Excuse me, sir. Can you make it full screen, the Matlab?
Okay. Yeah.
Yeah, now it's better. Thanks.
Okay. Maybe I can, also somehow trying to recall that there used to be some preferences. I could increase the font size. I can see preferences here. So editor fonts, and okay, maybe this will also make it easier to read. Okay, so I'm going to use this as my um, coloring agent, so to speak. So what I will do essentially is compare, say that V of t is equal to, or V of t I'm calling it my colored noise, okay, as 1 by 1 minus 0.9 times Q inverse into E of t. So you see, by coloring it, what has happened is that V of t now belongs to the old value of V of t, that is V of t minus 1. So I can write it like this: V of t is equal to 0.9 times V of t minus 1 plus E of t. You see, V of t now depends on V of t minus 1. So while E of t was completely white, you will agree that V of t is not going to be white, because that correlation, the autocorrelation function, will not look like that impulse or the direct delta. Okay, so let's see that, whether that is true or not. So I have over here uh, this numerator by denominator. Um, so let me just do an F9. Now, there is this function called transfer function. So if you do it, then it will make it just like how we were discussing in class. So you can see that your transfer function looks like this, exactly like how I wrote 0.101 minus 0.9 Q inverse. And now to get the colored noise, I'm going to basically run that. So I'll find out V of 1, V of 2, V of 3, and so on. So that is done in this way. So there's a command called filter in Matlab. So this comes from the signal processing toolbox, and given a numerator and denominator of a transfer function and the input. In this case, my input is E, as you can see here. But it could be any input. It could be a step input. It could be a sinusoid input. It'll just calculate the output and put it on your left hand side. So okay, we have that. So let's look at how colored signal looks like. I hope I have a hold on so that we can plot. Oh yeah, it was right here. And let's look at the signal. See, this is your correlated signal, the red one. So actually, if you have a trained eye, but not always possible. I have purposely chosen that to be 0.9, that it is a slowly drifting uncertainty. But if it is not so, or if I make it instead of minus 0.9, if I put it plus 0.9, you may not be able to catch it with an eye. Okay, and of course the amplitude is different. But the fact that one is white and one is colored, is to catch it with the eye. But using data processing tools like the autocorrelation, you can catch it very easily, or plotting the autocorrelation function, you very easily. So for example, if you, so this is X score, and I told you that, and max lag is basically telling me for how many values of tau should I do this computation, and we'll say that do it for 11. So let's just look at this. Okay, so X score is um, uh, I've given the signal E, and then I have given the signal V, which is R colored. Okay, and let's look at this autocorrelation. And teaching a course to students gives you enough time to put all these display, make it look a little fancy. And what you see is this. The top slide, and you see I put tau as negative and positive, because as I said, for autocorrelation doesn't matter, it's symmetric. So the Re of tau is on the top and Rv of tau is at the bottom. And you can see that although, as I told you, it was not that bad. You could train your eye to catch the autocorrelation. But by looking at the time signal, you don't see it. But the moment you start looking at expectations or some kind of moments, it becomes absolutely clear that one signal is completely uncorrelated, Re, and the other signal has a very, very strong correlation. Now you can imagine if V of t is 1, then V of t plus 1 is 0.9 plus some random component. V of t plus 2 is zero point 0.9 into that value, so it will be 0.81. And so by taking 0.9, it is slowly decaying. And the slow decay is evident in this Rv of tau. Okay, so you have now seen what a noise signal looks like, and this is the kind of noise signal that has corrupted your data. And after corrupting the data, that is the data you're trying to use to be able to find out what are A and B and C, those polynomials. Okay. So in this case, it is clear that, depending on the type of noise, you have to get the correct model type. And we will see shortly that, if you don't choose the correct model type, your using your residuals, we can tell whether your model is good or not good. Okay. All right, let's go to plotting power spectrum. Uh, so this SPA, spectral analysis, is the command which you can use, and many things in that. So I'll just see if I can plot the power spectrum without getting into too many details. So, people don't actually calculate power using the FFT of the autocorrelation, but they use an FFT of transform on the Y directly. Okay, so let me just look at this part. And okay, and this M is equal to 30, which is Hamming's window length, is something which is used to smoothen it. Because if I don't smoothen it, no, this will be very, very erratic. It will look very noisy. So on the top, is that supposed flat line, that point, that the blue one is of for the white noise, supposedly flat. Okay, but it is not. And that is because you have samples. As your number of samples grow, it will become more and more flat. And the red one is the power spectrum of the colored noise. And you can see that now in the blue line, and on the x-axis here is frequency. So you can think of each frequency corresponding to a sinusoid of a given frequency. So in the blue line, you can see that you have this at 0 is the steady state component. And then at 0.5, it is the sinusoid with a frequency of 0.5. At zero point 0.1, and this is the contribution of its power to that entire signal. So, a spectral analysis basically decomposes all the individual frequency components in that signal. And what you see is that even these higher frequency components, it will only go up to pi because this is a digital signal. So, all of them are equally represented in that power, the total power of that signal. Whereas when you look at colored noise, you see that only the low frequency components are represented and the high frequency components are all taken away. They don't contribute to that power. And that is because, you filtered it, it got filtered. So, this, uh, when we used to do this Bode plots, we used to say that, high frequency components get filtered. And the way I try to think about it is that, if if for example I have to, and this is not a good example, it's a very crude example, but if I have a fan in my room and I have a switch and I turn on that switch and turn it off at a very high frequency, the fan doesn't move, right? Because you don't give it time to even react to the, because the fan is heavy, it takes time to start rotating around, okay, and pick up speed, it takes time. Whereas on the other hand, if you had turned on the fan and then turned it off after enough time where you've given it time to spin, then it gets, its impact is felt. And the same thing is true over here. So the low frequency components get manifested in the power, but the high frequency components do not. Okay, so that was one thing that I thought I could discuss with you all. Let's go to the next thing on system identification, where we'll actually try to identify the polynomials. So another slide. Okay, So I'm going to take a second example where, let us generate data. So I'm going to assume that the process is simply some time series process. I'm not going to assume it's a physics process. Let that be our last step. So where I can handle or try to do it for the 4 tank process, let's just generate simple data ourselves and then try to identify that system. So I'm going to take an Armax process. What I did not tell you, is that in uh, there is a nomenclature, and when I write Armax, I really mean y of t is equal to b by a times u of t plus c by a times e of t. And when I write Armax, I will write the order of these polynomials. So I'll say NA, NB, and C. Okay. So for ARX, there is only A and B because C is 1. Okay. So for ARX, I will write, okay, can you go back up? So for an ARX, I will write A comma NB. Okay. So let me now assume an Armax model, and so I will go to this, and I had opened, I think it is this one. Yeah, I think it is. Okay, so this is my model. Okay, that A is 1 minus 1.7. B is, I told you always that the first leading is 0. So we start with B1 and B2, and then this is C. Now, when I try to go across, so let me write this model over there. So 1 minus 0.5, 0.7.
Excuse me, sir, you are not audible. Hello.
No audio is coming. Okay, okay. Thanks, Om Prakash. Yeah. Can Om Prakash?
Yes, sir. Hello. So in between, it's getting disconnected. Again,
Oh,
you
I'm
are
getting an
inaudible.
error message.
Yeah.
We're having problems connecting to the net.
Hello.
Yeah, again, is it frozen? Is it
Now it's fine, sir.
fine? Is it? You
Yeah.
can hear me. So I asked you, can you hear me?
That time I could not hear you, sir. Now it's fine.
Okay. 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 Yeah, I think I should not flip between the screens very, very quickly. Because, okay, great. Yeah. So see, I have written this Armax model. So I wanted to, see what is the nomenclature. So the nomenclature will be, this is an Armax NA is 2. What about NB? NB is 2 and NC is 1. This is an Armax 2, 2, 1 model. Okay. So what we will do is, no, we will assume some U. And one U which is very, very popular is known as the PRBS. And it is pseudo random binary sequence input. So it has certain theoretical properties which are very useful, and we can skip that. But I'm going to use this PRBS signal. So it's going to be a random signal which will have two amplitudes. It will be like low, low, high, and so on. Okay, so it will have just two amplitudes, and that is the signal that I will inject into this plant, and so this will be my U, and I will get y of t, which will be all over the place. And using this y of t and u of t, I will try to find out different models. So I will try to find out an ARX model. So remember, don't know the order. In reality, I will not know what the order is. So I'll just have to try out different things. Okay. I will try out an Armax model also. Okay. Can you see my cursor? Okay. Yeah, there seems to be some intermittent problems. Okay. All right. Yeah, so what I will to do is generate this YT and UT data and then find out some ABC, and at least when I use and try to find out RMX models, I will be able to see whether I can get these coefficients back. Okay, so let's try to do this. So I'm just run this, but I hope that idea is there. Let me just go back because there have been some connection problems and rephrase what we are trying to accomplish. So see, you need data. Without data, you can't do system identification. We saw that. So here, the data we will generate ourselves by assuming it's an RMX plant. So often we call the source of data as system or plant. So we'll assume that the data is coming from an RMX plant, which you will all say is not fair, but as a means of pedagogy, it's okay. And then we will have this Y and U. U I will generate using some very special signal called PRBS. And let's try to then propose that, for some order NA and B, let's find an ARX model, though we know in reality it came from ARMAX. Or for some orders ABC, let's find an ARMAX model and so on. And essentially we'll be able to show that, if the fit is, if your choice is not good, very often, it will show up in this RE of tau. RE of tau will tell you this is good or no good. Okay. So I'm going to go to my MATLAB screen. Okay. And start, okay. So the first thing, of course, is to define these polynomials because so that I can generate the data. So I have defined these polynomials now. I'm calling them A polynomial, B polynomial, C polynomial. I need to tell, how much, because, I need to generate data. So data will come from
Excuse me, sir. You are again inaudible.
the host of the meeting. Yeah, I think I'm back now. Am I back? Okay. Yeah. Really sorry about this. Maybe I should just go and buy some dongle or something like that. Okay, so let me try to continue. Okay, if it happens again, I will, we can probably I'll get some better connectivity platform. Okay, so I was trying to tell you that we have to generate this PRBS signal, and there is one command called ID input. So ID stands for these are system identification commands, and it can plot, it can do a lot of these commands are just based on their inbuilt commands, so you don't have to do anything yourself. Okay, was the Bode plot? Where is my figure 2? Oh, it did not plot it yet, so let's first plot it. And this is my ID plot. You see, it's a binary which has two, which has two amplitudes, -1 and 1. Made it full screen. This is my U of t. Now I will put this U of t into that Armax system, and let's get Y of t. So I have my ID data, and there are a lot of objects which are there. Let me just um, get this out and plot it. So we'll plot the output in response to this PRBS input. And you can see that this is my output Y. So you have with noise and without noise, and depending on how much variance you have given for the noise, and whether noise is is of what type, you can get this differently. So I look at it and I say that the noise is correlated. Maybe visually, if I take a shot at it, so the red one is without noise, but blue one is with noise added on top of it. Okay, now we are ready. So we have data. We have Y, which I just showed you, and we have U. Okay. So in the sysid toolbox, I can define an ID data object which will combine these. And so Y and U, my training set, so to speak, will be in one object. Okay. And that I'm calling it as ID data YU, input and output. Now the reason that software, whether it is Matlab or any other software, becomes so attractive is because the moment you have, you can very easily start generating these models. So you see, I have generated this model using this ARX. I'm telling here is my data, ID data YU, B to be 2, and this NK is the delay between Y and U. See, every time I wrote the models, I assume the delay to be 1. But you can, have it to be 2. So for example, Y of K is equal to some B times U of K minus 3. So you're saying that for 3 samples, the input or the input affects the output. was this is the performance of my ARX, which is a 2 comma 2, NA polynomial order 2, NB or polynomial order 2, and the higher order is the ARX model with polynomial order being 10. NA is 10 and NB is 10. Okay, so you can see that the um, the uh, the two and now you have to be able to make some kind of a decision whether this is good or this is not good. Example, when I look at it, it looks quite good. Okay, so I can blow this up, and we know that blue line and the red line are the ARX approximation of that nonlinear plant, or sorry, of that Armax plant, and they both look reasonable. Okay, but we can do a residual analysis, and there's a very nice command called resid. So if you apply the resid command, it tells for the first two sample or the first two samples or lags. So this suggests that the ARX 2 comma 2 is not good enough, and you have to increase the order of your ARX system. And if you were to use the 10 comma 10, it tells you where all the residuals seem to lie within what is the statistical zero, the 95% confidence band of being zero. And in this way, you could do your analysis or do system identification. So system identification, once you have your model, is extremely simple to do. You have, it's just call a command. And this is if I were to look at an Armax model itself. So if I say, no, I want to identify an Armax model. Now, all these models saved in your workspace, and you can just type, because each model is now just an object. So this is my MARX, and you can look at those polynomials. So hello.
Hello. Yes, sir.
Ah. I was again outed, no? I
Yes,
was
sir.
out
Yeah.
of the.
Yeah.
Okay. What was the last thing I had mentioned? I'll wind it up now because what was the last thing I had mentioned, Om Prakash?
You
I was doing the
done that.
residual
Yeah.
analysis, so I was
Yes,
showing
sir.
the residual for ARX, higher order ARX, and then the Rmax. And what I am now showing is, see that so what we had done was use a command to calculate these, and the command was simply ARX. For Rmax, the command was simply Rmax. For output error, the command is OE. For Box Jenkins, the command is BJ. So using that toolbox is extremely straightforward. And here is that um, we had a Rmax model from where we had got the parameters, and here is the identified plant. Oh, I'm yeah, sorry. Oh, I didn't save the. So here was that identified plant that I was trying to tell you. So the A and B polynomials for that ARX. So if you remember, it was for Rmax, this was 1. Of course, it is by definition. This was minus 1.5, and this was 0.7, if I'm not, or 0.6. And you can see that. So shall I just copy the plant also here? I'll just copy the plant. So this is the ARX model identified, and now I'm just going to paste the plant over here. So you can see that this was minus 1.5 and it got it as minus 1.47, not too bad. This was 0.7, so the A polynomial was 0.689, also quite close. Okay, and this was B and this was C. So this was the ARX model. In fact, when if you knew the true plant, then you could do a comparison. But in reality, you never know this true plant. And so what you have is only this A, B to go with. But it is comforting to know that they are not too far apart. Or if you were not happy with this, then you could get the high order ARX plant, which gave a better residual. So that was M, and you can see that this is the high order ARX plant. So this is A is a polynomial 10, B is a polynomial 10. Okay, so there are 20 parameters. So this is a highly over parameterized system. And finally, I will look at this Rmax, which we also identified using the data. And that was like this. So this Rmax 2 comma 2 comma 2 or 2 comma 2 comma 1 was actually quite good, was much better than that ARX. Let me just take these parameters and so this is my ARX which I identified. ARX identified. This is my Rmax identified where I have the uh, correct set of correct order. And this was the plant. So this is where the plant was. So you can see that if I model this as an Rmax, my coefficients are much closer to the true plant because I have been able to correctly model this noise. Okay. Now there are many properties that if you use an output error model, it can consistently identify parameters. There is all the statistics of biasness, consistency, small sample properties, large sample properties are all apply over here. But just to be able to play around and and get some working model very quickly, provided you have data, is something that these time series models can do. Okay, now because of this constantly this network problem, I'm a little uh, hesitant to showing you the four tank process, uh, because, but I would have liked to show you, that you could have done this with a physical process. So what I did here was a very cooked up process. It was an Armax plant. I could have done the same thing with a physical process where I have a four tank system. And in our lab, we have a real four tank system where people generate data and using time series models directly from data to a time series model, and then using that time series model to accomplish some other goal, whether it is monitoring or whether it is control, um, and so on. So let me, not proceed with this because of this network issue, and instead, maybe we can just discuss or take questions. Uh, I can make this available to you. The I can make uh, the MATLAB files available to you. Now these files, Octave does not have the same toolbox, and so I could not show this to you on Octave. Uh, so, are there any questions? So again, the kind of the big picture really is that you can take data, and from data you can directly arrive at a time series model. The utility is in control, model based control. We always like to have models which we can use to project how the plant is going to operate in future, and so such models are indispensable. In fact, if you go to a refinery and you say that I need a dynamic model to be able to, and you try to first principles, even let's say using Aspen, it is a very daunting exercise. Whereas when you have data, you can very easily come up with working models. So again, you don't get to know any insight, you don't have insight, but you do get models that you can start using in order to accomplish some goal. So it's a very, very enabling technology. I know that in for financial markets, times is used quite a lot. People use Arma. So if you don't know what is that input going in order to be able to predict what is the stock price, then you just do Y is equal to C by D times E. You don't have a U, and that is the type. It's known as an Arma model. Um, and so in this way, there are a lot of applications of this particular time series analysis. If there are any questions I can take, I need to recharge this. I think there is a problem. if there are any questions that we could answer or discuss. If you have any project in mind where you can use time series data, then the toolbox is extremely capable of doing. And not only the Matlab toolbox, as I told you, most of my students would do their projects in R or Python. You can accomplish almost all of this in those software. If there is no question, then because of this network issue, I will say we can conclude. I have a code for the 4-tank system where we do essentially the same idea that you have a data generated from the physics, and then you take that data and you identify the input-output time series models using exactly an ARX or an Armax. I will upload that on Moodle. Okay. So if there are no questions, I think let us conclude. So Om Prakash, we can conclude the session now.
Okay,
Once.
sir. Yeah.
Yeah. Okay. So good night, everyone.